Okay, accelerated pre-calc lesson 3.2, log functions and their graphs. So here are the lesson's key ideas. Okay, so let me propose a question to you. Let's say I ask you to find the inverse of the function f of x is equal to 2 to the x power. So this is an exponential function, right? So if we follow our steps for finding an inverse algebraically, you would replace the f of x with y. We switch the x and the y here, right? And then you would try and get y by itself using algebra. Well, there's nothing we can do algebraically to get y by itself, okay? So that's where logarithms come into play. So right here we can't get y by itself, so we can't find an inverse, right? So that's where this comes into play, logarithms. So by definition, basically it says if b to the y power, right? So we have some sort of exponential, right? Exponential function. If b to the y power is equal to x, well, this is equivalent to log base b, right, of x is equal to y, right? So whatever the base of the exponential is also the base of the log. But what happens is whatever the exponential equals, all right, it's over here, all right, for the log, and then this is equal to the exponent of the exponential function. Okay, so just kind of understand that these two right here, they switch spots when you're converting back and forth between forms. Okay, and we'll practice that later in a moment. It's actually pretty easy. So now that we know this solves our problem over here, because now we can get y by itself. Because if we change this to log form, it would be log base 2, right? Now whatever this equals, all right, log base 2 of x, right, is going to equal now the exponent here, which is going to be y. So we've solved our problem. We've gotten y by itself, right? So y is by itself. We change it to inverse notation, right, is equal to log base 2 of x. And that's how you say that, log base 2 of x. Okay? Now, there are a few conditions when you are in log form. The base will be greater than 0, so it will never be negative or equal to 0. It also won't be equal to 1, right? And the reason why is all these conditions, they really stem from just what we know about exponential functions that we talked about in 3.1. Okay, remember exponential functions, the base is not going to be 1, because 1 to any power is just going to be 1, right? The base has to be greater than 0, right? We can't have a negative here because we would get complex results if we plugged in values in for the exponent. And then x has to be greater than 0. The reason why x has to be greater than 0 here is because for the exponential, right, x is the answer. Remember, we had a horizontal asymptote, and we can never get this exponential to equal 0. That's why the graphs of our exponential functions, they never touch the x-axis, right? So that's where this is from right here, x is greater than 0. So all of these conditions in log form, they really just come from the ideas that we talked about for exponential functions. Okay. So next thing, let's kind of practice converting back and forth between log form and exponent form, right? So exponent form and log form, and this is really important. So for example, we know 3 to the 4th power is equal to 81, right? Well, if we change this to log form, this is the equivalent to log base 3 of 81 is equal to 4. Okay? So basically the exponent is just what the log equals, right? And then the answer of the exponential function, all right, is just the log. Okay, log base 3 of 81. Okay. Over here we have, let's say, 2 to the negative 5th power. Well, we know this is equivalent to 1 over 2 to the 5th, which is 1 over 32, right? So if we write this in log form, it would be log base 2 right? Because the base is 2 here. And then we have 1 over 32 is equal to negative 5. Alright, so remember, over here it can be negative, okay? We just can't have a negative over here. This value here always has to be greater than 0. Okay, it can't even be 0. Alright, so keep that in mind. Now let's practice going the other way around. Let's say let's say give you the problem in log form. Let's say log base 4 16 is equal to 2. Right? Well, in exponent form, what would this be in exponent form? It's just 4 to the second power, we know, is equal to 16. Alright, so real simple. So just know where the numbers go, alright? When you're converting from exponent form to log form, it's really, really simple. Okay? Okay, so let's take a look at this example here, where we need to evaluate some logs. Alright, so I'll do example A right here. So we need to evaluate this log right here when x is equal to 32. So log base 2, alright, x we say we want it to equal 32. So log base 2 of 32, we need to know what this equals. Okay, and when the numbers are nice like this, you guys can probably figure out what this is going to equal mentally, right? So basically the idea is this: 2 to some power has to equal 32. Well, we know 2 to the 5th power is equal to 32, and that would be our answer. Alright, so when the numbers are nice like this, most of the time you guys can figure out what the log is going to equal. Alright, it's not too difficult. And let's take a look at example B here. So we have log base 3, and they want x to be 1. So log base 3 of 1. So the idea is, well, 3 to what power is going to equal 1? Well, 3 to the 0 power. So this answer is going to be 0. So log base 3 of 1 is equal to 0. Alright, so this is equivalent to 0. Okay? Let's take a look at C. Log base 4, and we want x to be 2. Alright? So 4 to what power is going to give you 2? Okay, so this one's a little bit trickier. 4 to what power is going to give you 2? Well, if you think about it, if you take 4 and you square root it, doesn't that give you 2? Right? And this is the same thing as 4 to the 1/2 power. So our answer here is going to be 1/2, right? 4 to the 1/2 power, which means this, which means we're just square rooting the 4, is going to give us 2. Okay? D, we have log base 10, alright, and they want x to be 1 over 100, alright? So we have log base 10 of 1 over 100 is going to equal some value. Okay, well, first of all, we have a fraction over here, right? When you have a fraction over here, like 1 over some value or some sort of fraction, you know that you're going to have a negative exponent. Okay, so over here, negative 2, 10 to the negative 2 power is going to give you 1 over 100. Because if you think about it, 10 to the negative 2, that means 1 over 10 squared, and that gives you 1 over 100. Okay, so when the numbers are kind of nice like this, it's not too difficult to evaluate logarithms. Right? You're not going to, depending on the numbers, you're not always going to be able to find a nice easy answer. Okay, but sometimes you can. Alright, example 2 here. So we're going to practice just evaluating logarithms using a calculator. Okay, now your calculator, the log button on your calculator, that's what we call the common log, right? The common log has a base of 10. Okay, so every time you're working with a logarithm that has a base of 10, you're working with what we call the common log. Okay, and all calculators, the log button on there, the base is 10. Alright, so let me show you. Let's say we need to evaluate, so A here, log base 10, because we're working with a common log base 10 of 10. Right, now you could probably figure this out mentally. Right, we know that 10 to what power is going to give you 10? The answer is going to be 1. Okay, and then B right here, we have log base 10, alright, of 2.5. Well, this you can't really figure out mentally, right? It's a lot more difficult. Okay, so that's when a calculator comes in handy. Right? Now keep in mind, these are here when you're working with a common log, they're typically not going to show the 10. Okay, so when you just see the log and you don't see a base, you can assume the base there is 10. Okay, so from now on, every time we're working with a common log, if you don't see a base, you can assume the base of that log is 10. Alright, so I'm going to evaluate this right here, log 2.5 with a calculator so you guys see it. Alright, so here's the Inspire calculator. So what you would do is you would have to get to the log button, okay? And the log button's located right here. Alright, you would press Control. Alright, and then we have log, and then the base right here, we know the base is 10, and then we want 2.5. So log base 10 of 2.5 here. What does that equal? That equals 0.39794. And typically when you're working with logarithms, you will round it to 4 decimals. Okay, so over here you would say the answer is 0.39, and then since we round that, that'll be 79. Okay, so really easy to find the log with a calculator. Alright, so here are a few log properties that you should kind of memorize, and you don't really need to memorize them because it just kind of makes sense. Alright, so the first one, we have log base A, alright, of 1 is equal to 0, because anything, right, it doesn't matter what the base is, right, it could be, the base could be 2, could be a million, anything to the 0 power is going to equal 1. Okay, log base A of A is equal to 1. Well, this makes sense because whatever base you have, if it's to the 1 power, aren't you going to just get the same thing, right? So log base A of A is going to equal 1 because A to the first power is going to equal A, right? Log base A of A to the X is equal to X. And this is the one that I kind of want to just at least show you guys a little bit. So let me crop this. So why does this guy right here equal X, right? So let's say we have log base A of A to the X power. So we don't know what this equals, right? We don't know what this equals. Well, since we don't know what it equals, let's just call it X over here, right? Some unknown. If we change this now to exponent form, wouldn't we get A to the X power is equal to what? A to the X power. So we get a true statement, right? So that's why log base A of A to the X is just equal to X. Okay? And the last one, if you have basically if you have log base A of X is equal to log base A of Y, right? So over here, you can think of it as, well, if you just divide out the log base A, right, they just cancel each other out, right? Remember, this equal sign means equivalence, right? It means equivalence. Well, if log base A, right, of X is equal to log base A of Y, since this part is equal to this part, that means that the X and the Y have to be equal to each other. Right, then you know the X is just equal to Y. Okay, so let's kind of use some of these properties. So let's take a look at some of these examples right here. Alright, so let's take a look at some of these examples and use the log properties that we just learned. So A here, we need to solve for X. We need to find out what X should equal. Right? So this is real simple because if log base 2, right, if you have log base 2 on both sides, they kind of just cancel each other out, right? So you know the X has to be 3, right? Because you have to have a 3 here for these two sides to be equal. So we know X is just going to equal 3. Okay. Example B, we need to solve for X. So what should X be? Well, 4 to what power is going to equal 4? Well, you got to have 1 here, right? 4 to the first power will equal 4. So X is equal to 1, right? Super simple. C, We need to simplify here, so we need to simplify this, work it out. Well, we know that over here, log base 5 of 5x, we don't know what this is supposed to equal, right? So let's just say we put an x there. So now let's change this right here. Since it's in log form, let's change it to exponent form. We know that that's going to make it that 5 to the x power is going to equal 5 to the what? X, right? So 5 to the x is going to equal this value here, which is also 5 to the x. All right, so we have a true statement here. So we know this simplifies to equal x. Okay. And then example D here. So we need to simplify this. So let's make this equal to x, right? So this is in exponent form right now. I'm going to change it to log form. In log form, this would be log base 7, right? Log base 7, because that's the base. All right, of what? Of x is equal to, all right, log base 7 of 14, right? So once you've written this out, you're just going to see that, hey, the log base 7s basically cancel each other out. So in order for these to be equivalent, x has to equal 14 in this case. Okay? So that's how you use the log properties. And I like to kind of explain like this so that it makes sense. A lot of times, with some people, the way some people explain it, they'll just say, oh, if you have the log of some base, and if these are the same, they just cancel each other out, and you just get the answer x, right? But I kind of don't like that explanation because it doesn't make sense of things. Okay. Same thing here. If you have, if the exponent is a log, and the base of the exponential and the base of the log are the same, these kind of just cancel each other out, and then your answer is 14. But I don't like to explain things that way because it doesn't just make, I like to make sense of things, right? So when you make it equal x and you convert it to the other forms, you see that it's clearly, oh, x has to equal 14, and you understand why. Okay? Alright, so let's take a look at the graphs of exponential functions and their logarithms. So we've established that an exponential function and its logarithm are inverses of each other. Okay, so this function here and this are inverses. So since they're inverses, their graphs will be reflections across the line y equals x, right? And we've learned that in the past about inverses. Now for this exponential function, 2 to the x power, we know that if we just have some base to the x power, it's always going to cross through the point 0, 1, right? So that means that the inverse of this has to cross through the value 1, 0, okay? Because we're switching the x and the y. So it has to cross through the value 1, 0, right? So basically the idea is this: if you have the log of some base, it doesn't matter what the base is, of x, the graph, the generic graph for it is going to look like this. It's always going to look like this, okay? And let's notice right here that we have a vertical asymptote. A vertical asymptote right here at the line x equals 0. We have a vertical asymptote because this graph here is going to just keep on getting, getting closer and closer and closer and closer and closer, but it's never going to touch or cross this vertical asymptote. Alright, now over here though, it's going to just keep on, extending out, right, growing very, very slowly. Okay, so let's talk about the domain and range. Okay, so what's the domain and range, right, for this log function right here? Well, the domain, right, it looks like, what's our domain for this going to be? Is it how much of the x-axis does it cover? Well, it covers between, it's going to be more than 0, right? We can't be equal to 0. So greater than 0 to infinity, right? And then our range, all right, how much of the graph, how much of the y-axis does this graph cover? Well, it keeps on going down this way, and it's going to slowly keep on getting higher and higher over here. So it's going to cover from negative infinity to infinity, right? So this is for the log function. So let's make the connection here. For our exponential function, for this graph over here, for our exponential, what's the domain? The domain, all right, how much does this cover the x-axis? Well, it's going to keep on going forever this way, right? And it's never going to cross the x-axis right here. because we have that horizontal asymptote, and it's going to keep on getting wider over here. So our domain is negative infinity to what? Infinity. And then our range, what's the range of this exponential graph right here? How much of the y-axis does it cover? Well, it never touches the x-axis, right? So it's bigger than 0, and it goes to infinity, because this keeps on going up. So let's make the connection. So the domain, here's the domain and range for this exponential. And then remember, we talked about this, since we're switching the x and the y values, right? Because remember, the domain, aren't these really like your x values? Over here, the range are your y values. Since we're switching the x and the y values, since this log function is the inverse of this, if we switch these, you notice the domain of the exponential becomes the range of the log function, and the range of the exponential becomes the domain of the log function. Alright, so you guys have to see and make those connections, okay? And it's really nice how everything just kind of blends in together and makes perfect sense, okay? Alright, so let's kind of summarize what we know about the graphs of exponentials and their inverses, the logs. So if you have an exponential, okay, and b is greater than 1, if the base is greater than 1, right? So the graph would look like this blue graph right here. So the inverse of that would be this green graph, that would go through the point 1, 0, right? Because we switched the x and the y here, all right? And then log base b of x, and then b is greater than 1. Now you have an exponential function where b is greater than 0 but less than 1, right? That means that the graph, all right, remember, it's not going to grow, it's going to decay. So that's the blue graph right here. So the inverse of this would be the green graph for the log, right? So log base b of x, where b is greater than 0 but less than 1, right? You would get this green graph right here that goes through the point, right? If this is 0, 1, it's also going to go through the point 1, 0. Okay? So just try and remember the parent graphs of each one. If it's an exponential, what the parent graph looks like. So if it's an exponential function, if b is greater than 1, it grows exponentially, right? So slowly, then all of a sudden starts getting really steep. Okay? If b is less than 1 and it's an exponential, right, less than 1, greater than 0, then it's gonna decay, all right, and slowly get smaller, sorry. So it has exponential decay, right? And then the inverses, right? So just remember the graphs, the x's and the y values are just gonna switch, right? So the inverses are just gonna be reflections across the line y equals x. Okay, so they're just reflections across the line y equals x, right? So now let's talk about some shifts. So let's say we have the graph of log base 2 of x minus 3. Okay, so let's think about what this would look like. Oops. So now let's ignore this minus 3 part. If it was just log base 2 of x, right? We know that this graph here, well, it's gonna go through the point right here, 1, 0, right? It's gonna go through the point 1, 0, and basically it's gonna do this, right? Just so we get a general idea. All right, so we know it's gonna this graph here would look like this, right? Now you have a minus 3 over here, right? A minus 3. What does that mean? Well, the shifts are the same as all the other graphs that we work with. This minus 3 means we're going to move this graph to the right 3 times. So if we move it to the right 3 times, 1, 2, 3, this point here, okay, this point right here is going to be over here. All right, you move to the right 3 times, 1, 2, 3, this point right here is going to move over here. And then, so we know that this graph, now the important thing is, now you have to find the vertical asymptote, okay? So remember, there was a vertical asymptote right here, right, at x equals 0. Well, if you move it to the right 3 times, now there's going to be a vertical asymptote, right, at 1, 2, 3, at positive 3, right? So there's going to be a vertical asymptote right here. So when you graph it now, right, so when we graph this now, you know the graph's going to go down like this, and it's just going to grow right over here. Okay, so we're basically just taking this graph, we're shifting it to the right 3 times. 1, 2, 3. Okay, so we have a new a new vertical asymptote right here. It would be the line x is equal to 3. Okay, so let's take a look at another shift problem. Let's say we have log base, I don't know, 5, and then we have x plus 1 minus 4. Okay, so if we were to graph this guy, now remember the parent function, right? I always like to just show the parent so you guys understand right now. The parent graph, log base 5 of x, right? We know that, you know, it's going to go through the point 1, 0 right here, the point 1, 0. It's going to be like this, right? And then we've got the vertical asymptote right here. Well, if we have this plus 1 and this minus 4, what does that mean? Well, plus 1 means we're going to go to the left 1 time. Minus 4 means we're going to move to the down 4 times. So if we take this point and we move it to the left once and down 4, right? Well, that means that this point here now is going to be at, so we go to the left once and down 4. I'll go 1, 2, 3, 4. So this point is going to move right here, right? It's going to move right here. And then what's going to be our new vertical asymptote? Well, the vertical asymptote was at x equals 0, but since we moved to the left 1 time, we have a vertical asymptote at -1 now. X equals -1, we have a vertical asymptote, right? So this graph right here, when you graph this, it's going to be right down like that, and it's going to be going up like this. Okay, so really simple, nothing really complicated. Let's take a look at one more. Let's say we need to graph log base 1/2 of x minus 3 plus 2. Okay, so let me sketch a graph. And let me sketch the parent function, right, which would be log base 1/2 of x. So we know this graph right here is going to basically go through 1, 0, and it's going to be like this. Okay. Oops. So these values, -3 here means that we're going to move to the right 3 times, and +2 means we're going to move up 2. Right? So we're going to take this point, we're going to move it to the right 3 times. 1, 2, 3. So it's going to be right here. Okay? And then find the new vertical asymptote. Well, the vertical asymptote, I'm sorry, I forgot to move it up. So right 3, up 2. So let's say up 2 over here. And then the vertical asymptote, the new vertical asymptote, let's draw that in. So since we shifted to the right 3 times, there's going to be a vertical asymptote at x equals 3. So this graph, it's going to look like this. So we have going down. Right. And if you want to be real accurate and plot some points, you can. But the general idea is I just want you guys to be able to locate the new vertical asymptotes and to at least move this point right here, right, this 1, 0 point to its new location. Right? If you really want a really accurate graph, we can always plot some points over here to see where this would go and everything like that. Okay? Okay, the last thing we're going to talk about is the exponential function e to the x. Remember Euler's number 2.71828. Now remember, e is basically just a constant. It's 2.71828, Alright, 2.71828. So the graph of it looks just like any other exponential, alright, function where the base is greater than 1, right? So the inverse of e to the x is what we call the natural log, alright, the natural log ln x, alright, the natural log, alright, of x. Now the natural log, the base is always e. So you have to remember natural log, the base is always e. Okay? Well, so the inverse, since these are inverses, alright, the graph is just going to be a reflection across the line y equals x also. And since right here the exponential graph crosses at 0, 1, alright, so the inverse is going to cross at 1, 0. So basically this, the natural log x graph, it looks just like any log graph. It looks the same thing as a log graph where the base is greater than 1. Okay? So don't let that mess you up. Let's talk about some properties of natural logarithms, right? And they're pretty much the same thing as the properties of logarithms. Now, the natural log, remember the natural log, the base is always e. Well, e to what power is going to give you 1? Well, e to the 0 power will give you 1, right? Over here, the natural log, well, remember the base is e. Well, e to what power is going to give you e? Well, e to the first power, right? So natural log of e, alright, is equal to 1. Over here, remember the base is, alright, e. So the natural log of e to the x is just going to equal x, because if you change this if you change this right here to exponent form, it's really just going to be e to the x is equal to, and then what's this right here? E to the x, right? That's why the natural log of e to the x is equal to x, right? This exponent. And same thing down here. If you have the natural log of x equal to the natural log of y, well, the natural logs basically just cancel each other out, and x has to equal y. Okay. Also, this one over here, if you change this is in exponent form, if you change this to natural log form, it would just be the natural log of e, right, to the x, right, is equal to the exponent here. The exponent happens to be natural log of x, right? Now remember, they're not going to show, every time it's a natural log, they're not going to show the e. I'm just showing it right now so that you guys understand the base is e. So basically, that's why this is equal to x, because you have natural log of x is equal to natural log of x, which is true. Okay? Or like I said, you could just think about it, e and the natural log are inverses, so they just kind of cancel each other out, and then you just get x, as your answer. Okay? Alright, so let's talk about how to find the domain of logarithms. Okay? So here's the idea. We said that the domain of logarithms, it doesn't matter if it's a natural log or a normal log. This right here has to be greater than 0. It cannot equal 0, it cannot be negative, it has to be greater than 0. So just take whatever this is, right, and make it greater than 0. And then find out what values of x make that happen. So in this case, it would be x is greater than 2. So in interval notation, if x is greater than 2, if that's your domain, right, the way you would represent that, you would have 2 to infinity, right? Any value of x that's greater than 2, right, you can plug into this natural log. Okay? So basically the idea is just take whatever this is, make it greater than 0. Okay? Over here we have 2 minus x greater than 0. Let's find our domain. I'll just move the x over here, that makes it easier. So x is less than 2. So x has to be less than 2. So your domain is going to be negative infinity to positive 2. Okay, so x is less than 2. Right, so the way you represent that, think of it as a number line, right? Here's 2, our domain are all the values less than 2. Right, so this in interval notation represents this, right? Alright, let's take a look at C here. So we need this part here to be greater than 0. So you square root it, you get x is greater than 0. Okay, now be careful. This was, what kind of problem is this right here? It's an quadratic inequality. So you should remember that, hey, we've got to do, so basically this is the value that would make this equal to 0, right? So we have here, so since we've got an inequality and a quadratic, we need to test some points. Okay, so if you plug in, let's say -1 here, all right, and then 1. So if you plug in -1 into here, right, what are you going to get? +1. So it's positive here, right? If you plug in +1 here, you're going to get positive. So remember, since we want greater than 0, both of these regions are okay. So basically anything here can be your domain. Anything here can be your domain. It just can't be 0. So your domain is going to be -infinity to 0, union 0 to infinity. Alright, so don't forget the stuff from chapter 1, where, if you have a quadratic inequality, you have to make sure you do that number line test, right? Do the sign test on the number line. Okay? Alright, so let's use the natural log properties to simplify these problems right here. So we have the natural log of 1 over e. Now remember, for the natural log, the base is e. So just think of it this way: e to what power, right, is going to equal 1 over e? Well, that would be -1, because we know that e to the -1 power, that's going to equal 1 over e, right? We get this right here. Let's take a look at b. We have e to the natural log 5. So there's two ways you could do it. You could just use the idea that, hey, e and the natural log, they're just inverses of each other. So these can just cancel out and your answer is going to be 5. So that's probably the easy way, right? Now, if you want to make sense of this though, right? So e to the natural log 5, we need to figure out what this equals, right? So let's say we put an x there. If you change this to natural log form now, that would be natural log of the base e, right, of x is equal to this exponent, which is natural log of 5, right? So basically we have natural log e, natural log e. So these are the same, so we know this 5 and this x must be equal also. So that's why x is equal to 5. Okay, I kind of like this way because it makes sense of everything, instead of just, oh, we cancel this and we get this value here. Okay, but that's kind of the easy, short way to find the answer. C, we have 4 times natural log 1. Okay, so 4 times natural log 1. Well, right here, natural log of 1, what does this equal? Well, e to what power is going to equal 1? Well, that's 0. So this right here, natural log 1 is equal to 0. So we have 0 times 4, so our answer is just going to be 0. Okay? And then D right here, I'll just do it over here. 2 natural log e. So e to what power is going to equal e? Well, that's going to be 1. So natural log of e is equal to 1 times 2, so your answer is going to be 2. Alright, so real simple.